something is burning at the edge of the observable universe. It has been burning without pause for over 12 billion years. It outshines every star in our galaxy, combined by a factor of roughly 500 billion, and for 44 years, every telescope that photographed it thought it was a star in our own backyard. It wasn't a star. It wasn't even close. What is it that generates energy on a scale so extreme it rewrites the physical boundaries of what matter is allowed to do? Where did it come from in a universe that was barely a teenager? And why, in a cosmos we have been systematically cataloguing for over a century, did the single most powerful object ever found spend 4 decades hiding in plain sight, disguised as something unremarkable? The object in question is a quasar. Its name is J05294351, and in February 2024, a team of astronomers led by Christian Wolff at the Australian National University confirmed what the data had been whispering for years. This thing is the most luminous object the human species has ever detected in 13 billion years of visible cosmic history. The brightest thing we have ever seen, the most powerful engine we have ever found, and the story of how it was discovered, and what it means for everything we thought we understood about the early universe, is stranger and more unsettling than almost any science fiction. But before we can understand what J05294351 is, we need to understand what a quasar actually does, because the mechanism at the heart of this object is so violent, so thermodynamically audacious, that even physicists who have studied it for decades find it difficult to hold in their minds without a kind of vertigo. And there is a question buried beneath this discovery that nobody has yet fully answered. A question that keeps some of the world's best cosmologists awake at 3 in the morning, turning it over and over in their heads. How did a black hole weighing 17 billion times the mass of our Sun get that large in the first 1.5 billion years of cosmic time? Given everything we know about how black holes grow, it should be impossible. And yet, there it is. To understand why J05294351 stopped physicists mid-sentence when the data finally came in, you have to first appreciate the scale of ordinary cosmic violence. Because this object is not ordinary. Not by any measure. Our Sun is not a small star. It is a sphere of nuclear fire 1,392,684 kilometers in diameter, fusing 620 million metric tons of hydrogen into helium every single second and releasing the binding energy of that reaction as light and heat that reaches across 149.6 million kilometers of vacuum to warm your skin on a summer afternoon. That output, the total luminosity of our star, is 828 times 10 squared Avnev watts. This number is so large as to be essentially meaningless to the human nervous system, so let's try a different approach. If you could somehow harness the entire output of the Sun for 1 second, you would have enough energy to power all of human civilization at its current consumption rate for roughly 3.8 million years. 1 second. And yet, by the standards of the universe, the Sun is not particularly impressive. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, most of them far dimmer than the Sun, but the combined output is staggering. Roughly 10 cubifoot watts, or about 20 billion times the Sun's luminosity. When you look up at the night sky and see the faint smear of the galactic plane, you are seeing the combined light of hundreds of billions of nuclear furnaces, each of them burning through enormous quantities of fuel every moment. This is, by any reasonable human standard, an almost incomprehensible amount of light. J0529-4351 outshines it by a factor of roughly 25,000, let that land. A single object, one-point source of light, emitting 25,000 times more energy than the entirety of the Milky Way galaxy, with all its hundreds of billions of stars, every second of every day, for over 12 billion years. This is not a slight improvement over the competition. This is a different category of phenomenon altogether. The object sits in the constellation of Pictor, visible from the southern hemisphere, at a distance of approximately 12 billion light-years from Earth. When the light we now detect was first emitted, the universe was less than 1.8 billion years old, a cosmic toddler, still in the process of assembling its first large structures. The galaxies we know today did not yet exist in their current form. The structures that would eventually become the clusters and superclusters we inhabit were still being drawn together by gravity from the smooth, nearly uniform plasma fog that followed the Big Bang. In that young, churning, chaotic universe, something switched on, something that generated more light than the equivalent of 25,000 of today's mature galaxies. And it has not stopped. To find this object, you need to know roughly where to look, and then you need to be patient, and you need to be lucky, and you need to have the right instrument pointed at it at the right time. The universe is not organised for the convenience of the beings who live inside it, and finding quasars, genuinely identifying them in a sky full of billions of stellar objects, from galaxy clusters to nearby stars, is not a trivial task. Christian Wolff and his team at the Australian National University's Sky Mapper survey had been doing exactly this kind of systematic sky mapping for years, hunting methodically through catalogues of point-like light sources, looking for the specific spectral fingerprints that betray a distant, energetic core rather than a nearby quiet star. And here is where the story takes its first unexpected turn, because J05294351 was not found by a sophisticated algorithm trained on cutting-edge data. It was not picked up by an artificial intelligence system sifting through petabytes of spectral information. It was identified as a quasar by a human being, using a relatively modest 3-metre telescope at the Siding Spring Observatory in the rural New South Wales countryside, after decades of misfiling had left it sitting in plain view, unrecognised, in archival data going back to 1980. An automated system operated by the European Space Agency's Gaia satellite had looked directly at it in 2022 and declared, with 99.98% confidence, that it was a star, an ordinary, unremarkable point of light sitting somewhere in the Milky Way. It was not a star in the Milky Way. It was the most luminous object ever discovered by the human species, shining from the edge of the observable universe. And that paradox, the most powerful thing we have ever found, hiding in plain sight for 4 decades, is not merely an anecdote about the challenges of astronomical data analysis. It is a window into something deeply strange about the nature of extreme luminosity, about the limits of our machine learning models, and about the ways in which the universe's most extreme objects can masquerade as its most ordinary ones, because J05294351 was simply too bright to be a quasar. It was outside the known range of quasar luminosities, and because our classification systems are trained on what we already know, the machine looked at the data, found it impossible, and so reclassified it as something far simpler. There is a lesson in that, a lesson about the dangers of building our detection systems around the universe we already understand, rather than the universe that actually exists. But even understanding the scale of J0529-4351's output brings us to the deepest question this discovery poses, one that the February 2024 announcement did not fully answer, and that the September 2025 follow-up studies only made more confounding. How did this black hole grow to 17 billion solar masses in less than 1.8 billion years of cosmic history? And what does it mean that something this powerful existed when the universe was so young? For that, we need to go deeper into the engine. There is a phrase Christian Wolff used in his announcement of the J0529-4351 discovery that I have not been able to get out of my head since I first read it. He called it the most violent place that we know in the universe, not the most distant, not the most massive, the most violent. And when you understand the mechanism that produces the light, when you actually trace the physics from the infalling matter to the outgoing photons, you understand that this is not hyperbole. It is a precise description of what is physically occurring 12 billion light-years away. At the centre of J0529-4351 sits a black hole with a mass of approximately 17 billion solar masses, 17 billion times the mass of our Sun, compressed into a singularity surrounded by an event horizon. The Schwarzschild radius of such an object, the radius of the event horizon, the point of no return, would be approximately 5.1 times 10 cubic meters, or roughly 340 astronomical units. To put that in solar system terms, Neptune orbits the Sun at about 30 astronomical units. The event horizon of the black hole at the centre of J0529-4351 extends to more than 11 times the orbital radius of Neptune. It is, by an enormous margin, one of the largest black holes known to exist. But the black hole itself, strictly speaking, is not what generates the light. Black holes, by definition, do not emit electromagnetic radiation from within their event horizons. The extraordinary luminosity of J0529-4351 comes from what happens to matter before it crosses that boundary. As gas and dust and stellar material spiral inward under the black hole's gravitational influence, they do not fall straight in. They spiral because of angular momentum, the same physics that makes water spiral as it drains, except here the velocities involved are a significant fraction of the speed of light. This spiraling infall creates an accretion disk, a vast flattened structure of superheated plasma orbiting the black hole, growing hotter and denser as it spirals inward toward the innermost stable circular orbit, the last point at which matter can orbit without inevitably crossing the event horizon. The accretion disk around J0529-4351 has a diameter of approximately 7 light-years. To appreciate what this means, consider that the nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. The disk around this black hole extends outward for a distance greater than the distance between our Sun and our nearest stellar neighbour, in both directions from the centre. Samuel Lai, the ANU PhD student and co-author of the discovery paper, described it as what must be the largest accretion disk in the universe. This is not a modest claim, and it is supported by the physics. You need a disk this size to funnel matter into a black hole at the rate required to produce the observed luminosity. And the rate of matter consumption is itself extraordinary. J0529-4351's central black hole consumes the equivalent of 1 solar mass per day. Every 24 hours, the equivalent of our entire Sun, all its mass, all its hydrogen, all its nuclear fuel, is swallowed by this single object, 365 solar masses per year. In the roughly 12 billion years since this quasar appears to have been active, though it may not have been running continuously at this rate, the accumulated total is a number that strains the imagination. The energy conversion mechanism that produces the light from this infalling material is, from an efficiency standpoint, the most productive process in the known universe. Nuclear fusion, the process that powers stars and the process that powers every nuclear weapon ever detonated on Earth, converts approximately 0.7% of the mass of hydrogen fuel into energy via Einstein's equation, E·mc². This is extraordinary by any engineering standard. The mass-to-energy conversion efficiency of a quasar's accretion disk, depending on the spin of the black hole, can reach between 6 and 42%. The most rapidly spinning black holes, accreting efficiently, convert nearly half of all infalling mass directly into outgoing radiation. This makes a quasar's accretion process between 8 and 60 times more energetically efficient than the nuclear fusion that powers every star in the universe, approximately equals UL 6 to 0.42 wols. If fusion approximately equals 0.007, this extraordinary efficiency is what drives the luminosity. With 1 solar mass of fuel consumed every day, and an efficiency of order 10% or higher, the energy output is comparable to 500 trillion solar luminosities, an output so extreme that it violates an important theoretical constraint that physicists use to understand how such systems can function at all. That constraint is called the Eddington limit. Named for the British astrophysicist Arthur Eddington, who derived it in the 1920s, the Eddington limit describes a natural ceiling on how bright an accreting object can become before the radiation pressure of its own outgoing light blows away the infalling material that is feeding it. When an accretion disk becomes luminous enough, The photons streaming outward exert a pressure on the infalling gas and dust that opposes the inward pull of gravity. At the Eddington limit, these two forces, radiation pressure pushing out, gravity pulling in, exactly balance. If the object exceeds its Eddington luminosity, the radiation pressure wins, the accretion disk is disrupted, the fuel supply is interrupted, and the luminosity drops. In this sense, the Eddington limit acts as a kind of natural throttle, preventing black holes from simply eating everything around them without limit. J05294351 is accreting near the Eddington limit, pushing at the very boundary of what the physics permits. This is not impossible, but it is extraordinary because it requires the conditions to be essentially perfect. The accretion flow must be geometrically efficient. The angular momentum must be precisely calibrated to allow a continuous, uninterrupted spiral, and the environment around the black hole must be continuously resupplied with fresh infalling material at an almost inconceivable rate. Achieving this in the early universe, when the structures feeding these objects were themselves still forming, is one of the great unsolved problems in modern cosmology, and it raises three questions that this single discovery immediately forces into view. First, where did the 17 billion solar mass black hole at the centre of J0529-4351 come from? Second, given that the universe was less than 1.8 billion years old when this thing was already burning at peak luminosity, what does this tell us about the timeline of structure formation after the Big Bang? And third, this one is perhaps the most unsettling. Is there something our current models of black hole growth are fundamentally missing? While scientists in 2024 were publicly celebrating the discovery, privately, some of the most experienced theorists in the field were doing what scientists always do when the data contradicts the models. They were quietly beginning to rewrite the models. There is a specific kind of silence that falls in a seminar room when someone puts up a graph, and the data point sits in a place the theory says is impossible. It is not the silence of confusion. It is the silence of recognition, the moment when physicists understand that they are looking at something real, something measured, something that cannot be explained away by calibration error or instrument noise. And one version of that silence descended on theoretical cosmology in 2024 because J05294351 and the wider population of massive quasars discovered at high redshift pose what has become known, informally but with increasing urgency, as the seed problem. The seed problem goes like this. After the Big Bang, the universe spent its first roughly 380,000 years as an opaque, superheated plasma, a fog of charged particles so dense that photons could not travel freely through it. When the universe cooled enough for electrons to combine with protons and form neutral hydrogen, the fog cleared. This moment, called recombination, released the light we now observe as the cosmic microwave background radiation, the afterglow of the Big Bang itself, detectable today in every direction we look. After recombination, the universe entered a period called the Cosmic Dark Ages, a vast, cold, structureless expanse of neutral hydrogen, with no stars, no galaxies, no light of any kind. Gradually, tiny fluctuations in the density of that hydrogen, quantum variations amplified by inflation and then by gravity, began to collapse into the first structures. The first stars formed approximately 100 to 200 million years after the Big Bang. These were extraordinary objects, almost entirely hydrogen and helium, lacking the heavier elements that form in later stellar generations. They were potentially hundreds of times more massive than any star that forms today, burning briefly and brilliantly before dying in catastrophic supernovae or collapsing directly into black holes. These first stellar remnants are thought to have had masses on the order of 100 to 1,000 solar masses. Modest seeds, but seeds nonetheless. Here is where the seed problem crystallizes. If the first black hole seeds formed from stellar remnants around 200 million years after the Big Bang, and if they grew by accreting matter at or near the Eddington limit, the fastest physically permitted rate, then the maximum mass they could achieve by the time J0529-A4351 was already active, at 8 billion years post-Big Bang, is governed by a specific equation. The Eddington accretion timescale, the time required for a black hole accreting at the Eddington rate to double its mass, is approximately 45 million years, starting from a 100 solar mass stellar seed 200 million years after the Big Bang, accreting continuously at the Eddington rate for the subsequent 1.6 billion years. You could theoretically grow a black hole to roughly 10⁻⁻⁰ solar masses, 100 million to 1 billion solar masses. This already requires perfect, uninterrupted, maximally efficient Eddington rate accretion for the entire period, with no interruptions, no feedback-driven suppression, and no periods of quiescence. J0529-4351's black hole weighs 17 billion solar masses. This is 10 to 100 times more massive than the theoretical maximum achievable through continuous Eddington rate accretion from a stellar seed. The object, by our standard models, should not exist. MBH'd, MSeed, ETED, where 2 ed approximately equals 45 Maya. This is not a minor discrepancy that can be smoothed over with a slight adjustment to initial conditions. An order of magnitude gap between theory and observation is a crisis, and J0529-4351 is not alone in posing it. The James Webb Space Telescope, since its launch in December 2021, has been returning images of the early universe with unprecedented depth and clarity, and the data has been, to put it diplomatically, disquieting. Webb has found supermassive black holes at redshifts corresponding to the first few hundred million years of cosmic history, objects that, by the standard model of structure formation, had no business being as massive as they are, so early in time. The Harvard Center for Astrophysics described these objects in a 2024 analysis as black holes 10 to 100 times more massive than the relationships between galaxy mass and black hole mass would predict. This is what scientists call the overmassive black hole problem, and J0529-4351, discovered at redshift 3.962, is the most luminous and arguably the most extreme example yet found. It sits at the intersection of 2 crises: the seed problem, which asks how black holes could have grown so massive so quickly, and the Eddington problem, which asks how they could have sustained near maximal accretion for so long, without being disrupted by their own radiation. There are currently several candidate explanations, none of which is definitively confirmed. The first is the heavy seed hypothesis. Rather than forming from ordinary stellar remnants of 100 solar masses, the first black holes may have formed from the direct collapse of entire massive gas clouds, objects of 100,000 to 10 million solar masses that bypassed the stellar phase entirely and collapsed directly into black holes. These direct collapse black holes would provide seeds massive enough that even ordinary accretion could grow them to the observed sizes within the available time. The problem is that the conditions required for direct collapse, a pristine, metal-free environment, intense ionizing radiation to prevent the gas from fragmenting into stars, and just the right configuration of angular momentum, are exceptionally specific, and it is unclear whether they were common enough in the early universe to account for the observed population of overmassive black holes. The second hypothesis involves episodes of super-Eddington accretion, periods in which the accretion rate temporarily exceeds the Eddington limit, with the excess luminosity being trapped inside the infalling material rather than escaping outward. In super-Eddington accretion, the radiation pressure that normally throttles the inflow is overwhelmed by the sheer density of the inflowing material, and the black hole can temporarily eat faster than the Eddington rate allows. Recent simulations suggest that super-Eddington episodes could significantly accelerate black hole growth, potentially explaining objects like J0529-4351 without requiring extraordinarily massive seeds. The September 2025 follow-up observations of J0529-4351, which found that the gas around the black hole was being expelled at record speeds and yielded a revised mass estimate of approximately 1 billion solar masses, rather than the original 17 billion. A dramatic revision that itself introduced new questions, are consistent with a highly energetic, possibly super Eddington accretion episode that is driving powerful winds into the surrounding environment. The third hypothesis, more speculative but not ruled out, involves primordial black holes that formed not from stellar or gas collapse, but from density fluctuations in the very early universe, minutes or hours after the Big Bang, long before any stars formed at all. If primordial black holes with masses of millions or billions of solar masses formed in the first fraction of a second of cosmic history, they would have a roughly 13 billion year head start on the accretion process, comfortably reaching the masses observed today without violating any known physical law. The problem is that primordial black holes of this mass would have left observable signatures in the cosmic microwave background, and current CMB measurements constrain the primordial black hole population quite tightly. None of these solutions is satisfying. Each one solves part of the problem while creating new complications elsewhere, and this is the situation that J0529-4351 has placed cosmology in. Not the comfortable position of a discovery that confirms existing theory, but the deeply productive and deeply uncomfortable position of a discovery that breaks it. I find this genuinely exhilarating. The best science happens not when the data neatly confirms our predictions, but when it lands in a place the models say is forbidden and forces us to build better models. J0529-4351 is not a comfortable discovery. It is a disruptive one, and those are always the ones that matter most. But there is another dimension to the seed problem that has not yet fully entered the public conversation, one that connects the existence of objects like J0529-4351 to questions about the fundamental nature of the post-Big Bang universe, and to the possibility that the standard model of cosmology itself may require revision. For that, we need to look at what J0529-4351 is doing to the space around it. 7 light-years in diameter. Take a moment with that. 7 light-years, that is the physical width of the accretion disk around the black hole at the centre of J0529-4351. To drive across it in a spacecraft travelling at the speed of light would take 7 years. To cross it in the fastest spacecraft humanity has ever built, the Parker Solar Probe, which at closest approach reaches speeds of about 690,000 km per hour, would take approximately 33 million years. This disk, a swirling, superheated structure of plasma orbiting a gravitational singularity, is physically larger than the distance between our Sun and the nearest star in our neighbourhood, and it is not uniform. It is a gradient of extremity. At its outer edges, where gas and dust first begin their long inward spiral, temperatures are relatively modest, tens of thousands of degrees, comparable to the surface temperatures of the hottest stellar class O stars. Moving inward, temperatures rise exponentially. In the innermost regions of the disk, at the innermost stable circular orbit, temperatures reach millions of degrees, comparable to the interior of a star. At these temperatures, matter does not behave as we experience it in everyday life, or even as it behaves in the comparatively gentle environment of stellar fusion. Atoms are stripped of all their electrons. Nuclei interact at relativistic velocities. The plasma radiates at not just invisible light, but across the full electromagnetic spectrum, from radio waves through infrared, visible, ultraviolet, X-rays, and gamma rays. A roaring, continuous shriek of energy across 20 octaves of electromagnetic frequency. This is where the 500 trillion solar luminosities come from. Not from fusion, not from any form of nuclear burning, from friction, compression, and the inexorable conversion of gravitational potential energy into heat as matter spirals inward toward an event horizon, accelerated by the most extreme gravitational gradient in the known universe. The energy output is so extreme that it does not merely illuminate the surrounding galaxy. It restructures it. Quasars like J0529-4351 are now understood to be among the most important drivers of what cosmologists call feedback, the process by which the energy output of a growing black hole regulates the rate of star formation in its host galaxy and in the surrounding intergalactic environment. The radiation streaming outward from the accretion disk heats and ionizes the surrounding gas. The winds driven outward by radiation pressure, clocked in the September 2025 study of JO5294351 at unprecedented velocities, sweep infalling material away from the host galaxy, interrupting star formation across thousands of light years. At the poles of the rotating accretion disk, where the geometry focuses the energy output most intensely, some quasars launch relativistic jets, collimated beams of plasma accelerated to velocities exceeding 99.9% of the speed of light, extending for hundreds of thousands to millions of light years in both directions from the black hole, punching through the intergalactic medium like cosmic blowtorches. JO5294351 is classified as a radio-quiet quasar, meaning it does not produce the powerful, extended radio jets observed in some of the most extreme active galactic nuclei. But radio-quiet does not mean quiet in any meaningful sense. The energy output driving the observed winds and radiation in this object exceeds anything a radio-loud quasar would need to reshape its host galaxy entirely. The term radio-quiet refers specifically to the relative dominance of radio wave emission compared to optical and ultraviolet emission. JO529-4351 is quiet in radio relative to its own extraordinary optical and UV output, which is a bit like describing a tornado as relatively calm because it is not also accompanied by a hurricane. Now, there is a broader significance to the existence of J0529-4351, and it's kind that I think is often underappreciated in popular accounts of quasar discoveries. It concerns what these objects tell us about a specific epoch in cosmic history, one of the most important transitions the universe has ever undergone, an epoch called the Epoch of Reionization. After the cosmic dark ages that followed recombination, the first stars and quasars began to produce ionizing ultraviolet photons. Photons with enough energy to strip electrons from the neutral hydrogen that filled the universe. This process, which took place roughly between 150 million and 1 billion years after the Big Bang, fundamentally altered the state of all the matter in the universe. The universe transitioned from a neutral, largely opaque state to an ionized, transparent one, the state it remains in today. Without this reionization, the universe would look radically different. Instead of the clear, transparent intergalactic medium through which we observe distant quasars, galaxies, and the cosmic microwave background, we would be peering through an opaque fog of neutral hydrogen that would block much of the observable universe from view. Quasars like JO529-4351 are among the primary suspects responsible for reionization, their extraordinary ultraviolet output, hundreds of thousands of times more powerful than even the hottest young stars, could ionize enormous volumes of hydrogen around them, punching expanding bubbles of ionized plasma into the surrounding neutral medium. As these bubbles grew and merged, they gradually converted the neutral intergalactic medium into the ionized web we observe today. This means that the process responsible for making the universe optically transparent, the process that created the conditions under which all subsequent galaxy formation and star formation could proceed, was powered in significant part by objects like J0529-4351, burning at 500 trillion solar luminosities in the first 2 billion years of cosmic history. This is the point at which the stakes of this discovery become genuinely civilizational. J0529-4351 is not merely the most luminous object ever found. It is a window into the engine that drove one of the universe's most profound phase transitions. The moment when the cosmos went from dark to lit, from opaque to transparent, from formless to structured. To understand J0529-4351 is to understand a pivotal chapter in the autobiography of the universe itself. And there is still another layer, because as remarkable as J0529-4351 is, it is not the only contender for the title of the universe's most powerful object. There are other candidates, objects of different types, generating their energy through different mechanisms, operating at different timescales, that challenge our understanding in different but equally profound ways. To fully appreciate what J05294351 represents, you need to understand what it is competing against. There is a specific kind of joy that comes from finding something that has been lost, not misplaced exactly, but overlooked. Something that was always there, always visible, but which no one had yet understood. It is the joy of the archivist who finds a forgotten masterpiece misfiled in a storage room, or the paleontologist who realizes that the fossil their colleague excavated 20 years ago and labelled unidentified is, in fact, a species new to science. It is discovery compounded by a faint absurdity, the feeling that the universe has been quietly laughing at us this whole time. Christian Wolff knows this feeling well. He is an astronomer at the Australian National University's Research School of Astronomy and Astrophysics. Trained originally at the Max Planck Institute for Astronomy in Heidelberg, Germany, where he completed his PhD in 1999. For more than 2 decades, Wolff has been engaged in what he describes with genuine warmth as a treasure hunt, a systematic, painstaking search through the southern sky for the most luminous quasars accessible from Australian observatories. He is, in the most precise and unironic sense, a professional quasar hunter. The SkyMapper Southern Sky Survey, which Wolff and his colleagues operate using the ANU's 1.35 metre SkyMapper telescope at the Siding Spring Observatory in New South Wales, has been one of the most productive quasar detection programs of the past decade, cataloguing thousands of active galactic nuclei and identifying dozens of record-breaking or near record-breaking objects. J05294351 was different, and the circumstances of its discovery tell us something important, not just about this specific quasar, but about the fundamental limits of machine learning-assisted science, and about the ways in which the most extreme objects in the universe resist classification by systems trained on the merely extraordinary. The first images of the object that would eventually be confirmed as J0529-4351 were captured by the European Southern Observatory's Schmidt Southern Sky Survey in 1980. The Schmidt Sky Survey was a large-scale photographic survey of the southern sky, conducted using a 1-metre Schmidt telescope at the La Silla Observatory in Chile, designed to create a comprehensive photographic atlas of the southern heavens. In those photographic plates, the large-format astronomical glass plates that preceded modern digital detectors, black and white images developed in darkrooms by skilled technicians, J0529-4351 appears as a point of light, indistinguishable in any obvious way from the thousands of other point sources recorded in the same field. For 43 years it sat in those archival datasets, occasionally resurveyed by automated cataloguing systems, each of which classified it, confidently, as a star. The most recent automated misclassification came from the European Space Agency's Gaia satellite, the most precise astrometric observatory ever operated, a spacecraft that has measured the positions, distances, and motions of roughly 1.8 billion sources across the entire sky with sub-millisecond precision. Gaia's data release DR3, published in June 2022, included an automated analysis of J05294351. The algorithm examined the object's brightness, its apparent colour, its proper motion across the sky, and its parallax, the tiny apparent shift in position caused by Earth's orbit around the Sun, which reveals the distance to nearby objects. Based on all of this, the algorithm assigned a 99.98% probability that J0529-4351 was a star in the Milky Way. The irony is almost painful. The system was not wrong about the brightness. The object really is extremely bright, apparent magnitude 16 in the optical band, well within the range of a relatively nearby star. The problem was precisely that it was too bright to be a quasar in the known quasar catalogue. The models were trained on the existing population of known quasars, the brightest of which were significantly less luminous than J05294351. The most extreme known quasar at the time was so extreme that adding anything brighter to the model would have required a qualitative leap in assumptions, a leap that automated systems do not make. In 2023, Wolf's team at ANU was working through candidate quasars identified by SkyMapper, point sources that had shown up in the Southern Sky Survey with properties suggestive of active galactic nuclei, but which had not yet been spectroscopically confirmed. When they trained their telescope on J0529-4351 with the 2.3-metre ANU telescope at Siding Spring, what they got back was not the spectrum of a nearby F-type star in the Milky Way. It was a redshifted quasar spectrum, unmistakable in its broad emission lines, its ultraviolet excess, its characteristic pattern of ionized gas emission, and the redshift was 3.962, meaning the object was not nearby but 12 billion light-years away, and meaning the light being detected today was emitted when the universe was approximately 1.7 billion years old. Wolf has described the moment of this recognition in interviews, and there is something movingly human about it. He recalled feeling the familiar quickening that comes when the data begins to fall into place. When the spectrum on the screen starts to tell a story that is different from what you expected, he is not given to dramatic pronouncements. He is a methodical, experienced scientist who has spent 20 years finding and categorizing quasars, and who has a professional's immunity to premature excitement. The redshift of 3.962, combined with the apparent brightness of magnitude 16, was enough to suggest that whatever this was, it was not ordinary. Confirming the discovery required a significantly more powerful instrument, one capable of obtaining a high-resolution spectrum that could accurately measure the emission line widths, the continuum shape, and the precise luminosity. Wolf's team turned to the X-shooter spectrograph on ESO's Very Large Telescope, the 8.2-metre telescope at the Paranal Observatory in Chile's Atacama Desert, one of the most capable spectroscopic instruments on Earth. The X-shooter operates simultaneously across the ultraviolet, visible, and near-infrared bands, allowing a comprehensive spectral characterization of objects across a wide wavelength range, and it is specifically designed for exactly this kind of follow-up analysis of unusual or extreme sources. The VLT data confirmed what the ANU telescope had hinted at. J0529-4351 was a quasar. Its luminosity, corrected for the redshift and cosmological distance, placed it at approximately 500 trillion solar luminosities, 1.6 times 10 phi times the luminosity of the Sun, with an estimated bolometric luminosity of 10 Flagshrift ergs per second. The black hole mass was estimated, through reverberation mapping analysis of the broad emission lines, at 17 billion solar masses. The accretion rate was 1 solar mass per day. All of these figures place the object comfortably, if that word can be applied to anything about this discovery, as the most luminous quasar ever confirmed. The paper was submitted to Nature Astronomy in early 2024 and published on the 19th of February 2024. When Wolf was asked by journalists to describe the moment he realized what they had found, his answer was characteristic of the best scientists, measured, specific, and quietly honest. He described not the excitement of the discovery so much as the work, the careful checking, the rerunning of the analysis, the consultation with colleagues to ensure there was no instrumental artifact, no calibration error, no systematic bias that could explain away the extraordinary numbers. Discovery in science is not a moment of revelation so much as a process of elimination, of systematically ruling out the mundane explanations until only the extraordinary one remains. There is a detail about this discovery that I find personally haunting, and it is this. The light we detected from J0529-4351 left that quasar approximately 12 billion years ago, when the universe was 7 billion years old, when the Milky Way as we know it did not yet exist, when the Sun would not form for another 8 billion years, and when the atoms that would eventually constitute Christian Wolf, sitting in his office at the Australian National University, looking at spectral data on a computer screen in 2023, were not yet organised into anything recognisable as matter in the familiar sense. That light crossed 12 billion light-years of expanding, structuring, star-forming, galaxy-building universe, and arrived at a telescope in rural New South Wales, where a human being with 20 years of professional experience looked at the spectral output and said, "That is a quasar. That is the most luminous thing we have ever found." There is a version of that story that makes the universe feel vast and cold and indifferent, and there is another version that makes it feel, in some deeply irrational but undeniable way, as though the light was waiting. Wolf himself offered a reflection that cuts to the heart of why this kind of work matters beyond the science. He said that for a few minutes each day, working on the quasar hunt makes him feel like a child again, playing a treasure hunt, bringing everything he has learned over decades of professional astronomy to the table and finding something that no one has ever found before. In a field where the objects of study are billions of light years away, and the timescales of phenomena dwarf human civilization by factors of millions, that personal childlike sense of wonder is, I think, one of the most essential instruments in the astronomer's toolkit, because the question JZO529-4351 raises, how did you form, and what does your existence mean for the universe's first chapter, is not going to be answered by any single paper, or any single telescope, or any single generation of scientists. It is a question that will outlast everyone currently working on it, and the only way to sustain the effort required to eventually answer it is to remember, occasionally, why you started asking in the first place. Which brings us to the next question, the one that has been quietly building in the background of this entire story. J0529-4351 is the most luminous object ever discovered, but is it the most powerful? And what does the answer to that question depend on? Power is not a single quantity. In physics, power is the rate of energy release, energy per unit time. And this is where the question of the most powerful object in the universe becomes genuinely complicated, because different objects generate their energy at different rates, over different timescales, and through entirely different physical mechanisms. J0529-4351 is the most luminous persistent source ever observed, but the universe produces events, transient, catastrophic, brief beyond comprehension, that release energy at rates that make even J0529-4351 look modest. Consider what happened on October 9, 2022. On that day, at precisely 1317 UTT, a signal arrived at a network of space-based gamma-ray detectors. The Neil Gehrels Swift Observatory, the Fermi Gamma Ray Space Telescope, and several others, and within seconds it had saturated nearly every instrument pointed at the sky. The burst lasted for approximately 7 minutes of sustained peak emission, followed by a longer afterglow that persisted for weeks. It was designated GRB 22109A, and it was quickly given an informal title that has become its permanent identifier in the popular imagination, the Boat. The brightest of all time, GRB 221009A originated 9 billion light-years away, a cosmological distance but relatively nearby compared to J0529-4351, in the direction of the constellation Sagitta. Its source was a long gamma-ray burst, the type produced when a massive star exhausts its nuclear fuel, its core collapses to form either a neutron star or a black hole in a matter of seconds, and the catastrophic energy release drives twin relativistic jets of plasma outward along the rotational axis of the collapsing star. These jets, if they happen to be pointed toward Earth, produce the searing gamma-ray flash that our detectors record. The peak luminosity of GRB 22109A, measured by the CONUS wind instrument, was approximately 2.1 times 10 flick watts. To put this in context, J0529-4351's luminosity is roughly 2 times 10 cubic watts, about 1 trillion times less powerful than GRB 221009A at peak. At its maximum, the boat was releasing energy at a rate roughly 1 trillion times greater than the most luminous persistent object ever discovered. This is the difference between power and luminosity across time. J0529-4351 has been burning at 500 trillion solar luminosities for over 12 billion years. GRB 22109A burned at 1 trillion times that rate for 7 minutes, then faded. The total energy budget of the two events is comparable, It is the rate that differs by orders of magnitude. The boat was so luminous that it did something no previous astronomical event had been known to do. It ionized Earth's upper atmosphere from 1.9 billion light-years away. NASA scientists documented measurable disturbances in the ionosphere, the electrically charged layer of Earth's atmosphere between 60 and 1 kilometers altitude, caused by the burst's gamma-ray flux. For approximately 7 minutes, the boat toasted one side of our planet's ionosphere as no astronomical event in recorded history had done before. Had it been located not 1.9 billion light-years away, but within our own galaxy, say, within a few thousand light-years, the consequences would have been far more severe. Potential mass extinction from prolonged gamma-ray exposure, ozone depletion, and atmospheric chemistry disruption. NASA scientists estimated that an event of this intensity occurs once every 10,000 years in the observable universe. The probability of one occurring within lethal range of Earth in the history of complex life has been calculated as low but not negligible, and some researchers have speculated that previous mass extinction events in Earth's geological record may have been triggered by nearby gamma-ray bursts. Though direct evidence for this hypothesis remains elusive, the boat also produced photons of extraordinary energy. The Large High-Altitude Air Shower Observatory in Tibet detected photons from GRB 221009A with energies exceeding 18 tera-electronvolts, 18 times 10 squared electron volts, the highest energy photons ever attributed to a gamma-ray burst. These ultra-high energy photons presented a puzzle of their own, because conventional models of gamma-ray burst physics do not easily produce photons at these energies, and their detection has prompted significant theoretical work to understand the emission mechanisms involved. But if you want to talk about the most energetic particles, not the most luminous sources, not the most energetically sustained objects, but the individual particles with the highest energies ever recorded anywhere in the universe, then you need to move away from quasars and gamma-ray bursts entirely and turn your attention to something that has been puzzling physicists since 1991 and which received a dramatic new entry in 2023. On November 23, 2021, though it was not identified and published until 2023, the Telescope Array Surface Detector in the West Desert of Utah recorded the arrival of a subatomic particle with an energy of approximately 244 exaelectronvolts. To put this in perspective, 244 eV is 244 times 10 electron volts, roughly 40 joules of kinetic energy concentrated in a single proton, or proton-like particle, smaller than an atomic nucleus. This might sound modest in everyday terms, but consider that the most powerful particle accelerator on Earth, the Large Hadron Collider at CERN, accelerates protons to energies of approximately 13 times 10 squared electron volts. The particle detected by the telescope array had an energy 18 million times greater than anything the LHC can produce. This particle was named the Amaterasu particle, after the Japanese sun goddess, by the international collaboration that published the discovery in the journal Science in November 2023. It was the second most energetic cosmic ray ever detected, trailing only the extraordinary Oh My God particle of October 15, 1991, which arrived with an energy of approximately 320 exaelectronvolts, an energy equivalent to a macro-scale baseball thrown at 56 miles per hour, concentrated in a single subatomic particle. The Amaterasu particle is not merely a curiosity of extreme physics, it is a genuine scientific crisis, because when astronomers traced the trajectory of the particle back through the intergalactic medium, accounting for the deflections caused by magnetic fields along the path, they found that it appeared to come from the local void, a vast, relatively empty region of space adjacent to our galaxy group, which contains no known astronomical objects capable of accelerating particles to anything approaching 244 eV. There is nothing there. No active galactic nucleus, no nearby quasar, no known source of extreme particle acceleration that could account for a particle of this energy arriving from this direction. This is the ultra-high energy cosmic ray problem, It has been known since the Oh My God particle was detected in 1991, and it has grown more acute, not less, with every subsequent high-energy detection. There is a theoretical limit, called the Greisen-Zatsepin-Kuzmin limit, or GZK limit, on the maximum energy that a proton can retain while travelling through the cosmic microwave background radiation. Above a threshold of about 50 eV, protons interacting with CMB photons lose energy through pion production on a relatively short timescale, meaning that any particle above this energy must have originated within roughly 160 million light-years of Earth, or it would have been slowed below the threshold during its journey. The Amaterasu particle, at 244 eV, must therefore have a nearby source, and no nearby source, in the direction indicated by the particle's trajectory, has yet been identified. The ultra-high energy cosmic ray problem is one of the three great unsolved mysteries of high-energy astrophysics. The other two are the origin of the GZK violating cosmic rays in general, whether they come from active galactic nuclei, gamma-ray bursts, magnetars, or some entirely new class of object, and the question of whether the existing physics of particle acceleration is sufficient to explain these particles, or whether something beyond the standard model is required. This brings us to the third contender for the title of most powerful known object, the magnetar. A magnetar is a type of neutron star, the ultra-dense remnant of a massive star after a supernova explosion, with an extraordinarily powerful magnetic field. A typical neutron star has a magnetic field of about 10 squared Gauss, roughly 1 trillion times stronger than Earth's magnetic field. A magnetar has a field of 10 Phys Gauss or higher, 1,000 times stronger even than a typical neutron star. The magnetic energy density at the surface of a magnetar is so extreme that it fundamentally alters the structure of the quantum vacuum. Electron-positron pairs can spontaneously form from the vacuum energy. The refraction index of empty space becomes measurable, and the X-ray emission from the cooling surface is modulated by processes that have no analogue in any less extreme environment. On December 27, 2004, the magnetar SGR 1806-20, located approximately 50,000 light-years from Earth in the direction of the galactic centre, produced a starquake. A sudden reconfiguration of its crust released energy equivalent to all the energy our Sun will radiate in the next 150,000 years. In approximately 1/10 of a second, the gamma-ray flash from this event briefly outshone the full moon from Earth's perspective, despite originating 50,000 light-years away. It ionized Earth's ionosphere from across the galaxy. Had it occurred within a few tens of light-years of Earth, it would have been a mass extinction event. The question of which of these objects, J0529-4351, GRB 221098, the Amaterasu particle source, or SGR 1806-20, deserves the title of most powerful object in the universe, is not merely semantic. It is a question about what we mean by power, what we mean by object, and what we mean by universe. And the answer, I think, is that the question itself is the most productive part, because each of these extremes illuminates a different aspect of the universe's capacity for violence, a different limit of known physics, a different place where our models strain and crack under the weight of what the data demands. Science is not a linear march from ignorance to knowledge. It is a recursive process of provisional understanding, in which every apparently definitive answer generates a new generation of more precise questions. The discovery of J0529-4351 and its confirmation as the most luminous object ever detected was a landmark moment in February 2024. What happened in September 2025 was, in its own way, equally significant and considerably more confounding. In September 2025, a team at the Astronomy University published new observations of J0529-4351 using more advanced spectroscopic techniques, including data from the Gravity Plus instrument on the ESO Very Large Telescope Interferometer, one of the most precise optical instruments ever built, designed specifically to measure the masses of distant black holes through direct resolution of the broad emission line region. What they found upended the original mass estimate in a way that created as many new questions as it answered. The original 2024 paper had estimated the black hole mass at approximately 17 billion solar masses, derived primarily through single-epoch reverberation mapping of the broad hydrogen emission lines in the quasar's spectrum. This is a standard technique, calibrated on well-studied nearby quasars, and it had returned values in the range of 10 billion to 19 billion solar masses, depending on the specific emission line used and the assumptions built into the calibration. The 2025 follow-up found something different. Rather than showing the characteristic, broad, symmetric emission line profile expected from gas orbiting the black hole in Keplerian rotation, the rotational signature of the accretion disk itself. The spectral lines showed strong asymmetries and extreme velocities consistent not with orbital motion but with gas being actively expelled outward at extraordinarily high speeds. The gas was not orbiting the black hole, it was being blown away from it. When the analysis was revised to account for the contribution of this outflowing material to the emission line width, the width that had been used to infer the black hole mass, the revised mass estimate came in dramatically lower at approximately 1 billion solar masses. Not 17 billion, 1 billion. This is a significant revision. 1 billion solar masses is still extraordinary. It places J0529 4351's black hole firmly in the category of the most massive known black holes, comfortably above the mass of any stellar mass black hole by a factor of millions, but it changes the severity of the seed problem in a meaningful way. A 1 billion solar mass black hole at redshift 3.962 is unusual, but not beyond the reach of current theoretical models that incorporate super-Eddington accretion and moderate initial seed masses. A 17 billion solar mass black hole at the same redshift was genuinely inconsistent with all standard models. The 2025 revision therefore relaxed the theoretical tension somewhat, but it introduced a new and equally puzzling tension in its place. If the gas is being expelled rather than accreted, the quasar is undergoing what is called a powerful AGN wind or feedback event, a phase in which the radiation and pressure of the active nucleus drives material outward at velocities that can exceed a few % of the speed of light. Such winds are thought to be a key mechanism by which quasars regulate their own growth and the growth of their host galaxies. The outflowing gas removes the fuel supply, slows the accretion, reduces the luminosity, and eventually shuts the quasar down. In this interpretation, we may be observing J0529 4351 at a specific and transient moment in its life cycle, a brief, extraordinarily energetic feedback event during which the accumulated energy of billions of years of accretion is being vented outward in a single violent episode. The velocities measured in the outflowing gas were described as record-setting, the fastest quasar-driven winds ever observed, exceeding all previous measurements by a significant margin. This means that J0529 4351 is not merely the most luminous object ever found. It is also, as of 2025, the source of the most energetic known quasar-driven winds, outflows moving so fast that they represent a massive, ongoing injection of energy into the surrounding intergalactic medium, potentially reshaping the host galaxy and its immediate cosmic environment on timescales of tens of millions of years. This feedback mechanism is one of the central puzzles in modern galaxy formation theory. The problem, which has been recognized for decades but remains incompletely solved, is called the quasar feedback problem. Observations of galaxies in the local universe show a remarkably tight correlation between the mass of the central supermassive black hole and the properties of the host galaxy's stellar bulge. A correlation so tight that it implies a close coevolutionary relationship between the black hole and the galaxy, even though the black hole's event horizon is 1 billion times smaller than the galaxy itself, and the two systems interact only indirectly through the energy output of the active nucleus. This correlation, called the M-sigma relation, has been known since the late 1990s and has been one of the most robust results in observational extragalactic astronomy. The M-sigma relation implies that something connects the growth of the black hole to the growth of the surrounding stellar population. The leading candidate for this connection is feedback. As the black hole grows and the quasar phase proceeds, the energy output in the form of radiation and winds heats the surrounding gas, suppresses star formation, and eventually terminates both the quasar phase and the major star-forming activity of the host galaxy simultaneously. In this model, the quasar phase is not a side effect of galaxy formation, it is a regulatory mechanism built into it. The most luminous quasars, like JZO 529-4351, are the most extreme examples of this regulation, objects in which the feedback energy is so extreme that it restructures not just the host galaxy, but the wider intergalactic environment within billions of light-years. The September 2025 data on J0529-4351 provides what may be direct observational evidence of this process in action. If the fastest quasar winds ever measured are emanating from the most luminous quasar ever discovered, and if those winds are actively removing the fuel supply for further accretion, then we may be witnessing the beginning of the end of J0529-4351's active phase. The moment when the quasar begins to quench itself, shutting down the very engine that has powered it for perhaps billions of years. But here is the complication within the complication. The revised mass estimate of 1 billion solar masses, while reducing the severity of the seed problem, makes the observed luminosity even more physically extreme in a different sense. J0529-4351 is accreting at, or possibly beyond, the Eddington limit for a 1 billion solar mass black hole. The Eddington luminosity for a billion solar mass black hole is approximately 1.3 times 10 Hubble solar luminosities, about 13 trillion solar luminosities. J0529-4351 is radiating at 500 trillion solar luminosities. This is not at the Eddington limit. This is approximately 40 times above the Eddington limit. This brings us to the super Eddington accretion problem. As discussed in Chapter 3, the Eddington limit is a theoretical ceiling, not an absolute one, in certain physical regimes, particularly when the accretion rate is extremely high and the inflowing material is very dense. Radiation can be trapped inside the inflow rather than escaping outward, and the effective luminosity as seen from outside can exceed the formal Eddington limit by large factors. This is called super Eddington or hypercritical accretion, and there is observational and theoretical evidence that it occurs in certain classes of compact objects, ultraluminous X-ray sources in nearby galaxies, neutron stars or stellar mass black holes accreting at rates thousands of times above the nominal Eddington rate, are well-established examples of super Eddington accretion, where the super Eddington accretion can be sustained at the level implied by J0529-4351's revised 2025 parameters, 40 times the Eddington luminosity, for a billion solar mass black hole producing the most powerful quasar winds ever measured, is something that current theoretical models cannot definitively answer. The simulations required to model super Eddington accretion in massive black holes are among the most computationally demanding problems in astrophysics, involving magnetohydrodynamics, radiation transport, general relativistic effects, and feedback coupling over a vast range of spatial and temporal scales. The best current simulations struggle to simultaneously capture the physics of the inner accretion disk, the wind launching region, and the large-scale impact of the outflow on the host galaxy. There is also the question of what the Gaia misclassification tells us about the completeness of the known quasar catalogue. If an automated machine learning system trained on the best available data classified the most luminous quasar in the observable universe as a Milky Way star with 99.98% confidence, what does this imply about the objects that remain in such catalogues, unrecognized, because they are too extreme for the models to accommodate? How many J0529-4351 type objects might exist in the archival data, classified as stars or uninteresting optical sources, waiting for a human eye or a better trained algorithm to recognize them for what they actually are? The answer to this question is not currently known. What is known is that the bias is systematic and in a specific direction, the most extreme objects. Those whose properties fall outside the training distribution of any classification model are precisely the objects most likely to be misclassified. This is the classification horizon problem, and it has real implications for the completeness of any survey of the most extreme phenomena in the universe. Our maps of cosmic extremity are limited not by our telescopes, but by our imaginations, by our willingness to accept that the universe may produce things that are more extreme than anything we have seen before. The ESO's extremely large telescope, currently under construction on Cerro Armazones in Chile's Atacama Desert, will provide one partial solution. With a primary mirror 39 meters in diameter, the ELT will be capable of resolving and spectroscopically characterizing objects at cosmological distances with a sensitivity and precision that exceeds current instruments by a factor of roughly 100 in light gathering power. Christian Wolff has specifically identified J05294351 as a priority target for the ELT's first light program and the Gravity Plus upgrade on the VLTI, designed explicitly to measure the masses of distant quasar black holes through direct interferometric resolution, will provide the most precise measurement of J05294351's black hole mass yet achieved, potentially settling the question of whether the 2024 17 billion solar mass estimate or the 2025 1 billion solar mass revision more accurately reflects the true mass of the system. There is also the question of gravitational lensing, a possibility flagged in the original ESO press release, but not definitively ruled out. If there is a massive galaxy or cluster of galaxies between Earth and JZO 529-4351, aligned along the line of sight, the gravity of that intervening mass could act as a cosmic magnifying glass, focusing and amplifying the quasar's light beyond its intrinsic brightness. This effect, gravitational lensing, is not merely hypothetical. It has been observed in numerous other quasar systems, and the most dramatic known example, J043947.081634.1.7, appeared briefly in 2019 to have a luminosity of 600 trillion solar luminosities, before analysis revealed that a gravitational lens was amplifying its light by a factor of roughly 50, reducing the intrinsic luminosity to about 11 trillion solar luminosities. The team has analysed the available imaging data for evidence of lensing and has found no convincing candidate lens object in the available data. The current interpretation is that the luminosity of J05294351 is intrinsic rather than lensing amplified, but definitively ruling out lensing requires higher resolution imaging than is currently available. Ideally, resolved imaging of the source structure from the ELT or from a space-based high-resolution facility. If it turns out that J05294351's luminosity is amplified by lensing, the intrinsic luminosity would be lower, potentially by a large factor, and the object might be demoted from the top of the luminosity record. If lensing is definitively ruled out, the luminosity stands, and the theoretical implications are, if anything, more severe. The question of whether J05294351 is truly the record holder it appears to be, or whether it is an extraordinary object whose apparent extremity is partially a trick of cosmic optics, is one that should be definitively resolved by the ELT within the next decade. And the answer either way will be scientifically consequential. Meanwhile, three open questions hang over the entire enterprise like storm clouds. First, what is the true mass of J0529-4351's black hole, 17 billion solar masses, as the original emission line analysis suggested, or 1 billion solar masses, as the 2025 outflow analysis implies? Second, what is the true intrinsic luminosity of the source, absent any possible gravitational lensing contribution? And third, the deepest and most consequential question, how did whatever is at the centre of J0529-4351 come to be, in a universe barely 1.7 billion years old? The answer to this last question is not merely about one extraordinary quasar. It is about the origin of all supermassive black holes, about the conditions of the early universe, and about whether the standard cosmological model is adequate to describe the first few billion years of cosmic history. The story of J0529-4351 is in one sense a story about the past, about light that left its source 12 billion years ago, about a black hole that was already burning at near-peak luminosity when the universe was a fraction of its current age, about a discovery that was hiding in plain sight for 44 years. But the implications of this discovery point forward, not backward. They point toward the next generation of observatories, the next generation of theoretical models, and, most importantly, toward the next generation of questions the extremely large telescope, when it achieves first light, currently projected for the late 2020s, will be the largest optical near-infrared telescope ever built. Its 39-metre segmented primary mirror, comprising 798 individual hexagonal segments each 1.4 metres across, will collect more light in 1 hour than any previous telescope can gather in an entire night. Its adaptive optics system, designed to compensate in real time for the blurring effects of Earth's atmosphere, will deliver images approaching the diffraction limit of a 39-metre aperture, a resolution roughly 16 times sharper than the Hubble Space Telescope. For objects like J0529-4351, the ELT will make possible spectroscopic analyses of extraordinary precision. Measurements of the accretion disk structure, the black hole mass, the composition and kinematics of the outflowing winds, and the properties of the host galaxy, all at a level of detail that is currently inaccessible. The Square Kilometre Array, the world's largest radio telescope array, currently under construction simultaneously in South Africa and Western Australia, will add a complementary radio wave perspective, while J0529-4351 is radio quiet in the technical sense, still emits measurable radio flux, and the SKA's extraordinary sensitivity will allow detailed mapping of any radio-emitting structures associated with the system, including any jets, lobes, or extended emission features that might not be detectable with current radio facilities. More broadly, the SKA will conduct deep surveys of the radio sky that are expected to discover thousands of new radio-quiet and radio-loud quasars at high redshift, dramatically expanding the known population of luminous AGN in the early universe and providing the statistical basis for understanding whether J0529-4351 is a unique extreme outlier or the most visible member of a substantial population of similarly luminous objects that current surveys have simply not detected. The Nancy Grace Roman Space Telescope, NASA's upcoming Wide-Field Infrared Telescope, with a field of view roughly 100 times larger than the Hubble Space Telescope, will conduct wide-area sky surveys with a depth and aerial coverage designed specifically to find rare extreme objects, exactly the class of object that J0529-4351 represents. Roman's sensitivity to infrared light makes it particularly suited to detecting quasars at the highest redshifts, where the ultraviolet and optical emission is redshifted into the infrared band. Population studies of the most luminous quasars across cosmic time are a core component of Roman's scientific program, and the telescope is expected to find dozens to hundreds of new objects comparable in luminosity to J0529-4351 within the first few years of operations. The theoretical side of the story is equally active. The past 2 years, following both the JWST results on overmassive early black holes and the J0529-4351 discovery, have seen a rapid acceleration in theoretical work on early black hole formation and growth. Numerical simulations of the early universe have become more sophisticated, incorporating radiative transfer, magnetic fields, and more realistic prescriptions for stellar feedback, and they are beginning to produce scenarios in which the formation of very massive black hole seeds, though still requiring specific and somewhat rare conditions, is not implausible within the standard cosmological framework. The Super-Eddington accretion pathway, once considered exotic, has moved closer to the theoretical mainstream. with several groups reporting simulations in which black holes can grow by factors of thousands in relatively short periods through periods of hypercritical inflow. And then there is the possibility, speculative, but taken seriously by a growing minority of cosmologists, that the standard model of cosmology itself may require modification. The lambda CDM model, which describes a universe dominated by cold dark matter and a cosmological constant driving accelerated expansion, has been extraordinarily successful at describing the large-scale structure of the universe, the pattern of temperature fluctuations in the CMB, and the observed abundances of the light elements. But it was calibrated on the universe as we observe it today, and there is increasing evidence that the early universe, the first few hundred million to few billion years of cosmic history, may have produced structures and objects more rapidly than the standard model predicts. This tension between the observed population of massive luminous early structures and the predictions of the best-tested cosmological model is not yet a crisis in the same sense as the seed problem for individual quasars, but it is accumulating, with every Webb observation of an unexpectedly massive galaxy or unexpectedly bright quasar at high redshift, with every revision like the J05294351 mass estimate that forces a reassessment of how we infer black hole masses from spectral data. The theoretical community is being pushed toward a more honest accounting of what the standard model can and cannot explain. There is also an entirely different frontier opening in the study of extreme cosmic objects, one that was effectively inaccessible until September 2015, when the LIGO experiment detected gravitational waves for the first time. Gravitational waves are ripples in the fabric of spacetime, produced by accelerating masses travel at the speed of light and carry information about the source, its mass, geometry and dynamics, encoded in the wave amplitude and frequency profile. The merger of two supermassive black holes, which must occur when galaxies merge, as the black holes at their centres spiral together under gravitational radiation and eventually coalesce, would produce gravitational wave signals of extraordinary power and extremely low frequency, far below the detection range of current ground-based detectors like LIGO and Virgo. The Laser Interferometer Space Antenna, LISA, is a space-based gravitational wave detector currently under development by the European Space Agency, scheduled for launch in the 2030s. LISA will be sensitive to gravitational waves in the millihertz frequency range, precisely the band where supermassive black hole mergers produce their signals. When two black holes of the class found in J05294351 merge, two objects each weighing billions of solar masses, spiraling together and coalescing in a final cataclysm that releases more energy in gravitational waves than all the stars in the observable universe emit in light over the entire merger duration. LISA will detect the event in exquisite detail, measuring the masses, spins, and orbital parameters of the merging pair with precision unavailable through any electromagnetic observation. The era of multi-messenger astronomy, the simultaneous observation of cosmic events in gravitational waves, electromagnetic radiation and particle emission, is in this sense only in its earliest infancy. The full picture of what objects like J05294351 truly are, how they formed, and what they do to the universe around them will not be assembled from any single telescope or any single observational technique. It will be assembled from the combined data of telescopes and detectors that operate from radio waves to gamma rays, from the ground and from space, and from instruments that detect not photons but space-time itself. The generation of astronomers currently in graduate school, the students who are today learning the spectroscopic techniques that Christian Wolff used to confirm J0529-4351, will be the first generation to have all of these tools simultaneously available. ELT will be operational, LISA will be operational, the SKA will be operational, the Roman Space Telescope will be returning data, and the questions that J0529-4351 has forced into focus: how did this form? Why is it so powerful? And what is it doing to the universe around it? will be the questions they spend their careers answering. There is one more question that needs to be addressed before we close, one that brings together everything we have discussed and asks it in the starkest possible terms. J05294351 is 12 billion light-years away. The light we see from it left before our sun existed. The universe has had 12 billion years to change since then. What is J05294351 doing right now? Is it still burning? Is it still the most luminous object in the universe as it currently exists? And if the quenching mechanism implied by the 2025 outflow data has proceeded as expected, has J05294351 already faded, already consumed its fuel supply, already silenced its own engine, already transformed into whatever a quasar becomes when the feast is over? The answer is that we cannot know. Light travels at a finite speed, and the universe has a finite age, and the light that is currently leaving J05294351, if anything is still leaving it, will not arrive at Earth for approximately 12 billion more years. In 12 billion years from today, the Sun will have exhausted its hydrogen fuel, expanded into a red giant that engulfs Mercury, Venus, and possibly Earth, and collapsed into a white dwarf. The Milky Way will have merged with the Andromeda Galaxy to form the Milkdromeda Elliptical Galaxy. The universe will be approximately 25.8 billion years old, and at that moment, if any intelligence exists in the galaxy to detect it, the signal currently leaving J0529-4351 will arrive, and that intelligence will learn whether the quasar is still burning, or whether it has gone dark. We are seeing it as it was. We are thinking about it as it might be now, and we are building the tools to understand what it means. This is what it means to do astronomy at the edge of the observable universe, to study a past that no longer exists, in order to understand a present that we cannot see, in preparation for a future that no one currently alive will experience. There is something strange and quietly profound about the way this story ends, or rather does not end. J05294351 has not been explained. The seed problem has not been resolved. The question of how a black hole weighing billions of solar masses came to exist in a universe barely out of infancy remains open. The 2025 mass revision changed the numbers but did not change the fundamental mystery. The classification horizon problem, the unsettling realization that our best automated systems will systematically fail to find the most extreme objects because those objects fall outside the training distribution of every model we build from existing knowledge, has not been solved. What we have is a discovery, not a destination, a discovery that has repositioned the map. I want to sit with one specific number before I close, because I think it carries a weight that the rest of the statistics, for all their extremity, perhaps do not. In the southern hemisphere night sky, J05294351 is visible as a 16th magnitude point of light in the constellation Pictor. This is faint, well below the threshold of naked eye visibility, but observable with even a modest amateur telescope, given dark skies and a suitable filter. The light reaching your eye, or your telescope sensor, has been travelling for 12.4 billion years. It left its source when the universe was 1.7 billion years old. Every atom in your body did not yet exist in its current form when that light began its journey. The solar system had not yet formed. The Milky Way was still assembling, and yet here it is, arriving at your detector, carrying within its spectrum the fingerprints of the most violent place we know. The broad emission lines of hydrogen and carbon and magnesium, ionized and Doppler shifted, and Eddington stressed, whispering the same physics that governs a hydrogen atom in a school laboratory, magnified to scales that break the comfortable scale invariance we usually assume the universe possesses. The universe is not scale invariant. J05294351 is the proof. There are places where the physics operates at an intensity so extreme that the mechanisms we understand perfectly well in laboratory and stellar contexts, gravity, accretion, radiation pressure, magnetic fields, produce outputs that seem to violate the rules those same mechanisms follow at lower energies. The Eddington limit is a real physical law, The GZK limit is a real physical law, and yet both appear to be violated, or at least strained to their breaking point, by objects that the universe has produced, and that we are only now beginning to catalogue. The most luminous thing we have ever found has been visible, unrecognised, since 1980. It was classified as a star by one of the most sophisticated observational programs in human history. It required a human being with 2 decades of professional experience, a 2.3-metre telescope in rural New South Wales, and a sequence of methodical follow-up observations culminating in data from an 2-metre instrument in the Chilean desert to be identified for what it actually is. And having been identified, it immediately began to resist clean explanation, generating a mass controversy within 18 months of its announcement, producing record-breaking outflow measurements that redefined our understanding of quasar feedback, and sitting at the intersection of at least 3 major unresolved problems in modern cosmology. This is, I think, what the universe has been doing to us since we first built instruments sensitive enough to ask questions about the deepest sky. Every generation of telescopes reveals a universe more extreme, more structured, more paradoxical, and more magnificent than the previous generation could accommodate. The Hubble Space Telescope showed us galaxies in the first billion years. Webb showed us galaxies in the first few 100 million years. The ELT will show us the first stars. And with every step backward in time, the picture becomes simultaneously more detailed and more puzzling. J05294351 is a threshold crossed, not a mystery solved. There will be another record breaker. There always is. Another quasar more luminous, discovered hiding in archival data by another patient and methodical scientist who had learned to look past what the algorithms expected. Another object that should not exist by the standards of the models that preceded its discovery. Another 44 years of misfiling waiting to be corrected. The universe is not trying to be understood. It is not arranging its most extreme objects in conveniently observable locations, labelling them with unambiguous spectral signatures, and waiting for our telescopes to find them. It is indifferent to our taxonomies. It produces phenomena at scales and energies that our instruments were not designed to detect, and that our models were not built to accommodate. And it continues to do so regardless of whether anyone is looking. That is not a failure. That is the condition. The history of science is not the history of progressively complete answers. It is the history of progressively better questions, questions precise enough to be tested, specific enough to be falsified, rich enough to outlast the generation that formulated them. The question J05294351 asks, "How did you form?" will occupy some of the best minds in cosmology for decades. The answer, when it comes, will almost certainly raise a deeper question still, and that deeper question will outlast the answer that produced it. We are the generation that found the brightest light. We have not yet understood what kindled it. And perhaps that is exactly where we should be, standing at the edge of the observable universe, looking at something 12 billion years old, turning it over in our minds, and feeling the specific and irreplaceable sensation of not yet knowing. Science doesn't always give us endings. Sometimes it gives us horizons, and the horizon of J05294351 stretches further than anything we have seen before. Further than the reach of our best telescopes, further than the span of any human lifetime, further than the edge of any model we have yet built. It burns at 500 trillion solar luminosities, 12 billion light-years away, in a universe that has been keeping its most extreme secrets in plain sight all along. Go find them.